Hi Year 10, so today we're looking at analysing chromatographs, and the learning outcomes for today, just the three, is be able to recall and describe safely how to carry out the method for a paper chromatograph, describe how to calculate the RF values, and describe the uses of chromatography. So if you are bored of listening to my voice or just want some supplementary material, please feel free to go to the Caboodle textbook, and you can look up this on page 142, 143, where there are some nice diagrams, also with some worked examples if you need some support doing those. So you've probably done this a zillion times. However, if you're a bit bored, you can get some do this at home quite easily with kitchen towel and some felt tips, not Sharpies, felt tips. So first of all, we're going to have our piece of paper, and we're going to draw our pencil line across the middle, okay, because pencil is insoluble and won't separate out. And then what you do is you put along your pencil line, good distance apart, some different coloured inks, and then you just dip water, or just literally just put water along the bottom edge, and what you will see is that the water will travel up the paper, separating out those dyes. So this is what you've done in school, but this time when you did it in school, you used filter paper. And we can use chromatography for a whole range of reasons. You might have done it at primary school with Smarties, you put them in Smarties. Some of you who may have seen those Elf on the Shelf hacks at Christmas, where they do it with Skittles, where they put a big rainbow of Skittles and then they put water in the middle and all the dyes come out. Chromatography is commercially used just to see what pigments or inks or colourings are within foods. And my group did this where we compared American M&M colourings to UK M&M colourings to see if they were any different, because actually you can have all sorts of crazy stuff in your M&Ms in America, and therefore we compared the two to see whether or not they were the same. And they weren't. So it can be used to distinguish between pure and impure substances. It can be used to distinguish whether something is a mixture or just made of one single dye or ink. It can also be used to work out and match different colours to a known standard to decide what colours have been mixed or which pigments have been mixed to make that colour. And it usually produces 2 or more spots. However, in some cases it will produce only one. And we talk about having phases. So the stationary phases, in which the paper and the chromatography is very uniform and it's an absorbent paper. And the mobile phase is the solvent, and that moves through the paper. So the stationary phase refers to the paper that isn't going anywhere because it's just sitting there. However, the mobile phase is when we add the solvent, and that solvent moves up through the paper. Now that solvent usually is water. However, if you were using Sharpies, you'd want to use something like acetone or ethanol to make it soluble. So different dissolved substances in a mixture are attracted to the 2 phases in different proportions, and this causes them to move at different rates. So simplistically, we've got our beaker, we've got our bit of paper, we've got our pin. You might have used a paper clip and a splint. We've got our water, we've got our ink spot. Notice that our ink spot is above the water, because if you put it below, it will then the ink will go down into the water. And we've got an equipment list. Now on our equipment list, we've got capillary tubing, and they are really, really fine little straws. And if you dip them into the ink and then dot them onto the paper, they act just a bit like a pen. But it's a good way of getting a really accurate, sharp spot. Safety. Now, obviously, some people are violently allergic to food colourings, and therefore we do need to be wary of that. And if you know that you have a food allergy, you do need to wear gloves. Glassware, especially the capillary tubes, they're really fragile, and they do break. And if they do break, it's quite a sharp glass splinter, and obviously that could potentially be an A&E trip. And lastly, which goes without saying, but they're always one of you, do not eat the food colouring. So here is my method. Now you'll notice that my method is slightly longer than normal. However, what you do need to do is be able to recall that method in the simplistic terms and explain how to do it. Now, I think that this one is quite a simple one to recall. So what I would do, if it was me, I would divide my paper up into 6, and then I would draw myself a little picture all the way along. Do it like a cartoon strip. Do something different today, okay? I know some of you are doing it with revision cards. Fantastic idea. But this is a very wordy method. Try and reduce those chunks down so that we've got some more recall. So, here we are. That's exactly what we do. So, I'm going to skip to point 6. So it says carefully lower the chromatography paper into the beaker, taking care that the pencil line is above the water. Leave the water line until the water line or the solvent front has passed the last colour spot. Okay, so that's when, if you look at the yellow dot on the right-hand diagram, is that when the yellow seems to stop moving, but there is still clear liquid moving up the paper, that's when you would then take that out. And at that point, we would take that out to dry, okay, and we still need to hang it, because if you put it down onto a flat surface, the colours will then start to mix up, okay. But before you do that, you need to just gently mark with the pencil where the solvent got to, because we do need to take that as a measurement. So we're going to be calculating the RF value, and the RF value is important because it means that if, I don't know, somebody does it with a small piece of paper and somebody else does it with a longer piece of paper, or somebody leaves it for a longer period of time on a longer piece of paper, that you can compare those RF with retention factors values and see whether or not they are comparable. You also, if you were doing this commercially, so as your job or in the industry, you would compare those RF values to a book of known RF values, and it would tell you the dyes and inks that are being used, and you would be able to then work out the content of your pigment or food colouring. So the RF value is the ratio, and you're going to calculate that by dividing the distance the spot travels up the paper by the distance the solvent has travelled. So you do need those top measurements. And this is where the error comes in, because if you haven't marked when the solvent front has got to where it has at the right time, then you might not get a very accurate reading. If, for any reason, you also distance moved by the substance, you need to make sure you measure from the same part on the dot each time again, because some people will measure from the bottom, some people will measure from the top, and that will give you a whole variety of different reasons that you need to be different errors that will be occurring. So here's a worked example for using compounds A and B using the chromatograph opposite. This picture, your final bit with your dots on it, is called the chromatograph. So A, the RF value is 8 divided by 12, which gives me 0.67. And B, the RF value is 3 divided by 12, which gives me 0.25. Now you'll notice that my RF values in both cases are below 0, and it should always be below 0. If you've gone below, if it's above 0, you've multiplied them the wrong way round. So what they want you to know is, can you demonstrate your understanding here? So answer these 5 questions for me. Pause the slide now. So here's the answers. Definition of a solvent: a substance which can be used to dissolve a solute or a solid. What is the mobile phase? It's the solvent carrying the substance. What is the stationary phase? The chromatography paper. Explain why the pencil should not pen should be used to mark the base. This is a really common question, okay? I've lost count of the number of times it turns up, so I would really make sure that you've got this answer nailed. Pencil is insoluble in water, and pen and ink would spread out with the chromatograph in the experiment. And lastly, calculate the retention value of X. So you notice again, 7.5 divided by 9.7 gives me 0.77, below 1. and you can look at this video, this exciting practical being filmed at this YouTube channel, which I have put in the link on Show My Homework. Take care, and I will see you soon.